Now that we know how to graph in polar coordinates, we're going to address the next interesting question, that is, how do we do calculus in polar coordinates? And first, let's talk about motivation. Why do we need to do calculus? Well, first of all, polar coordinate system is just another coordinate system. So whatever we learn to do with Cartesian graphs, we naturally want to do the same in polar coordinates. So it doesn't matter if you have two axes, x and y, or you have a single polar axis with a pole. Once you have a curve, whether it's a part of a graph in a Cartesian or part of a polar curve in polar coordinate system, we may want to know what will be the equation of the tangent line. So that's a good question. How do I find equation of the tangent line? And we find it by finding the slope first. But how do we find the slope? Well, the slope is the derivative, and derivative is calculus. Now, on the other hand, we may want to know the length of this path that is described by polar curve. Length of a curve is also calculus. And finally, we may want to know the area under the curve, which is also calculus. So we have some of these basic questions, such as what is the slope, what is the arc length, what is the area, and we can only answer these questions if we know how to do calculus in polar coordinates. And turns out that doing calculus in polar coordinates is actually relatively straightforward if you understand the relation between the equations in polar coordinates and parametric curves. So first, let's recall that the type of curves that we will be looking at can be expressed as a function of r in terms of theta. So for example, we'll be looking at the curves produced by the equation maybe like this, and theta is the input variable here, so we may have some domain restricting the values of theta. But where do we go from here? The next thing I want to talk about here is I want us to ask again all these important calculus questions, just so we know what are we going to be doing next. And I want to remind you what the answers to those questions are in Cartesian. We can call it Cartesian calculus and calculus with parametric equations. So when it comes to finding the slope of the tangent, in Cartesian calculus, we just adopt the following notation. In polar, I'm sorry, not polar, but parametric equations, here's the setup. We know that derivative can be found by differentiating y with respect to t, and then differentiating x with respect to t and finding the ratio. We also know how to find the second derivative. For curves defined parametrically, we know the answer as well. It is, again, it looks really crazy here, but it's not that crazy once you understand the notation. we know how to find the area between the graph and an axis. So I'll use x-axis as an example here, but we use integration to answer that question. So we also know the answers to these questions for curves defined parametrically. We also know how to find the arc length. The formula for the arc length was actually quite simple in general, so let me put it here on the side. In Cartesian calculus, we only needed to learn how to interpret ds as a square root of 1 plus the derivative of x squared with respect to x, and we learn also how to interpret ds in parametric equations. And finally, the area of the surface of revolution. We also had a very simple formula, so we would integrate over some domain of integration, but let's say we're rotating around the x-axis, and then we'll simply just have 2 pi, and here we put the radius of rotation, which could be simply y ds. So everything that we learned above how to interpret ds applies here as well. So the question is now, can any of this be used when it comes to polar curves? So can we take this formula maybe and turn it into a formula for the derivative of the polar curves? Can we take this formula and turn it into something useful? And the answer, luckily for us, is yes to most of these questions, but we have even a better solution to some of these problems. We're just not going to care about it much. So for example, the idea is if you know how to find the first derivative, once we learn that, we're really not even going to go this far, right? So we're not even going to try to find the second derivative because we understand it's just going to be the derivative of the derivative. But since the expressions will get somewhat complicated, we're not going to go that way. Now, when it comes to the area between the graph and the x-axis, we're actually going to switch it up a little. So I'm going to, I don't know what to draw here, but instead of, notice how the task of finding the area between the graph and the x-axis is very specific to Cartesian coordinate system. We don't have x-axis in polar coordinates, so this is going to be a problem, which we will address by simply considering a different area. But the arc length is actually something that we will learn. And once we learn how to figure out the arc length, the problem of finding the surface area of a solid of revolution will be very simple conceptually, so we're not going to go that way. We're just going to make a mental check mark in our mind, and conceptually we would be able to advance that far, but we're just not going to. So the only question is now, how can we turn our knowledge of parametric equations into the knowledge of polar curves? And the answer is very simple. We're going to learn how to parametrize r theta. And what does it mean to parametrize r theta. That means we're going to introduce a parameter, and we're going to write two equations, one for x and one for y, and put it together and call it parametric equations. So recall that we have the following relations between x, r, and theta. X squared plus y squared equals r squared. Tangent theta is equal to y over x, and also x is equal to r cosine theta, and y is equal to r sine theta. So which of these relations we can use to parametrize r theta? Well, it looks like this set is basically made exactly for the task of parametrizing. So for any the polar curve given by an equation in this form, the following will be true. X can be expressed as r cosine theta, but remember, r is a function of theta. So if I replace r with the expression provided in the definition of r here, then I'm going to end up defining x as a function of theta. Similarly for y, if I replace r with that expression of theta, I will be able to define y as a function of theta. And therefore, the following set of equations is called the parametric equations. Or the parametrization of this polar curve. And that's what we needed. So where do we go from here, you may ask, and the answer is we now, once parametrized this curve, we can apply everything we know about parametric equations to polar curves. So let me show you a quick example here how to parametrize an equation. So if we have the following curve, then we can parametrize it. X will be r theta times cosine theta, so it's going to be r theta cosine theta, but r theta is 2 cosine theta according to this definition. And similarly, y of theta will be r theta times sine theta. And we can write it as sine of 2 theta. And what we have now is a parametrization of the curve. So that means if we use Desmos to graph, we can use either one of these representations of this curve. So let's try. Graphing this in Desmos gives us a circle centered at 1, 0. And let's graph the parametric curve. So we had cosine squared. It was 2 cosine squared. Instead of theta, I'll be using letter t here. and let's put comma and sine of 2t. And notice how if we match the domain of t with the domain of theta in the original equation, we're going to get exactly the same curve. And if you want to actually visualize this whole process of, like, you know how we said before that the parametric curves are dynamic, so here's an alternative way. We can copy this and replace t with some other letter and add a slider a, then it's going to make it into a point, and you can provide the same exact domain and then just move a according to the steps. So now we can turn this all off and just keep an eye on the dot. So as a increases, as the parameter increases from 0 to pi, this is what happens. Now that we know how to parametrize the curves in polar coordinates, next we'll learn how to do calculus in polar coordinates.